teach you will guide you. Constant, never left, just changes.
Welcome to another virtual physics lecture. Today we're going to be discussing conservation of energy, specifically focusing on mechanical energy, so be sure to take good notes and let's begin. Let's review what we know so far. Based on our previous lectures, we mentioned that law of conservation of energy states that energy cannot be created and that it cannot be destroyed. In fact, energy is actually only converted from one form to another. We also talked about the different forms of energy and examples of them going through energy transformations, such as this one where radiant energy is converted into electrical energy, then converted into mechanical energy, thus demonstrating how energy is conserved. Well, this is the case for all energy types, and in this video we're going to be focusing primarily on mechanical energy and how it is also conserved. Remember that mechanical energy may be seen as potential energy, in which the object, such as this boy, has the potential to move due to his position at the top of this hill. Once the boy starts to move from the top of the hill, he now has mechanical energy, which is known as kinetic energy due to his motion. Remember that because these are all forms of energy, the units that we use to describe potential and kinetic are joules. Okay, so let's take a look at what this little boy's up to. He's on top of a tree branch and he has a lot of potential energy due to his mass, gravity, and height. Well, in order for us to determine exactly how much energy he has, we would need to use this formula. Notice that potential energy is abbreviated as PE, and it equals mass times gravity times height. Let's say that this little boy's mass is 30 kilograms, and gravity we know is 9.8 meters per second squared. Lastly, let's say that he is 20 meters high on that tree. All we would have to do is multiply 30 times 9.8 times 20, and this would give us 5,880 joules. Now remember, for the purposes of our class, we tend to round the value for gravity to 10 meters per second squared. So don't get confused when you see 9.8. It still means the same value. We're just rounding it to 10. So what does 5,880 joules of potential energy actually mean? It means that if this branch were to break, the boy is going to fall with a potential energy of 5,880 joules that's going to get converted into kinetic energy, causing him to fall down at a high velocity. So let's say that we were to determine the velocity of the boy before he fell, and it was 19.8 meters per second. What would be his kinetic energy? Well, we would have to use this kinetic energy formula. Notice, kinetic energy is abbreviated as KE, and it equals mass times velocity squared divided by 2. The mass of the boy was 30, and the velocity we said was 19.8. Okay, so let's plug it into the formula and solve. First, let's square 19.8. This gives us 392. And we multiply by 30, which gives us 11,761. Then we're going to divide by 2. This ends up giving us 5,880 joules for kinetic energy. Notice that this is the same value that the boy had as his potential energy when he was on top of the tree. And then when he fell, all that potential energy got turned into kinetic energy, thus conserving all the mechanical energy. Now that we know how to determine potential and kinetic energy, it's essential that we understand one main concept, which is that mechanical energy must be conserved. Therefore, the potential energy that the tire swing once had when lifted will be converted into kinetic energy, back and forth, and so on, thus conserving the total mechanical energy. So we've been going back and forth with the terms mechanical, potential, and kinetic. But let's take a look at how all of these relate to one another. Basically, mechanical energy, which is abbreviated as ME, is the total energy of potential and kinetic energy. For instance, this roller coaster shows 100 joules of total mechanical energy in yellow, and as the roller coaster moves, the potential and kinetic energies change based on the roller coaster's position. But notice how when you add up both of these energies, they always equal the same 100 joules of total mechanical energy. Okay, so let's take a look at another example. Let's look at the skater. When the skater is at the top of the ramp, he has the highest amount of potential energy due to his height, which is shown in blue. And notice he has 0 kinetic energy, which is shown in green. So if we wanted to find out the total mechanical energy, we would just add up the two and it would give us the yellow bar, which is mechanical energy. Now look at what happens when the skater moves towards the bottom of the ramp and his potential energy in blue decreases and his kinetic energy in green increases. But the total mechanical energy, which is in yellow, always stays the same. Notice that when the kinetic energy is the greatest, potential energy is at 0 and seen at the lowest height of the ramp. Then when the greatest amount of potential energy is seen, the kinetic energy is at 0, which is at the highest point of the ramp. Let's take a look at this next example to see how mechanical energy is conserved when potential and kinetic are converted in this roller coaster. First, let's start at the top of the roller coaster. Let's say that this cart has 100 joules of potential energy, and as we mentioned before, the highest point would give us the greatest amount of potential, but would give us 0 kinetic energy. So if we were to add up the two, we would end up with a total of 100 joules for mechanical energy. Based on the concept that mechanical energy is conserved, we could say that this roller coaster cart will have 100 joules of total mechanical energy at any position throughout the roller coaster. This means that the kinetic and potential may change throughout the roller coaster, but the mechanical will stay the same. Okay, let's look at the second position. Since the height is half the amount of the previous position, that would mean that the potential energy would be half as much as well. Thus, potential energy at this point is 50 joules, meaning that kinetic energy would also be 50 joules in order for the total energy to stay as 100 joules. Okay, next position. We know that the lowest height will provide the highest kinetic energy, which would be 100 joules, and give us 0 for potential energy. Then lastly, in this position, if we were to say that kinetic energy is 75 joules, that would mean that potential energy must be 25 joules in order for the total mechanical energy to be 100 joules. What would be the potential energy of the skater at the bottom of the ramp? Well, because the height at the bottom of the ramp would be 0, that means that potential energy would also be 0 joules. Okay, now let's look at kinetic energy. Well, the mass is 60 and the velocity is 8. So we square the velocity and end up with 64. Then multiply it with 60, giving us 3,840. Then we divide by 2, giving us 1,920 joules of kinetic energy. Potential energy was 0. When we add up the two, we end up with 1,920 joules of total mechanical energy. This means that the skater will have 1,920 joules total mechanical energy at any other position on the ramp as well. Okay, let's look at the second position. Here we see that the height is 1 meter, which means that potential energy equals 60 times 10 for gravity and times 1 for its height, giving us 600 joules of potential energy. Since we know that the total mechanical energy must be 1,920 joules and 600 joules were for potential energy, then that must mean that kinetic energy at this position was 1,320 joules. Now let's see what the velocity would have been at this position with this amount of kinetic energy and the mass of the skater being 60 kilograms. First, let's move the 2 to the other side by multiplying it on both sides, giving us 2,640. This will equal 60 times velocity squared. Okay, now let's divide by 60 on both sides, giving us 44 equals velocity squared. Now we just need to get rid of the squared by square rooting both sides, giving us a velocity of 6.6 meters per second. Lastly, let's look at this final position in which we see that it is at the top of the ramp, thus potential will be the greatest and kinetic energy will be 0. Because kinetic energy is 0, we know that velocity must then be 0 as well. Okay. Now all we need to solve for is final height of the ramp. To do this, we must set up the equation with what we know. Potential energy at this position is 1,920 joules, and the mass is 60, and we know gravity is 10, leaving us to solve for height. Okay, when we multiply 60 times 10, that gives us 600. And to leave h by itself, we must divide 600 on both sides, giving us 3.2 meters. Okay, so that's it for this video. Hope you guys took good notes, and I'll see you in class.
Ability to work heavy, constant, never